There's this delta that appears in both of these equations. And in the first one, the one acting on m and j seems to be acting at infinity, where we've defined the ADM mass and the angular momentum. But the delta A is a perturbation at the horizon. And so it seems like perturbations at infinity and perturbations at the horizon are interacting. There's weird kind of non-locality. What's going on here? There doesn't seem to be any sort of mapping between these two different kinds of perturbations. So basically just what I want to say today about this is just show you how you map them back and forth. And then the second thing to say, which becomes a little bit more interesting once we look at this mapping, is to ask how do the A's in the first and second laws relate. So they both represent the area in some sense or other, but the way that one gets to them and what you might take them to represent might be different for the two different laws. So the particular version of the first law that I want to look at is one given by Iyer and Wald in '94, in which they define something called the Wald entropy, which has been extended to lots of other theories. And in fact, when they give it, they define it for any diffeomorphism covariant Lagrangian theory. So this is really, in the end, going to be a theorem about just geometric Lagrangian theories. But there's a small restriction that they put on it, which I want to take off, or I'll show you how we can take off later on. So we're going to look at a theory which has Lagrangian that depends on the metric and the symmetrized covariant derivatives of the metric, and some collection of matter fields psi, similarly there, covariant derivatives. But we have a number of terms with a little circle on top, and this is going to represent fixed background fields of some kind or other. And I'm going to explain how, on this definition from this picture, the perturbations don't act at the horizon at infinity, they act over all of space-time. And then I'm going to say a couple things about how this might be made, sense might be made of this. So the Iyer and Wald paper proceeds in two steps. First, you show that you can always rewrite a Lagrangian like this in terms of just the metric and its Riemann tensor, the Levi-Civita connection, the matter fields, and they say you can drop out the dependence on the background fields. When this is true is going to depend on what exactly you take general covariance to be, and I'll say something more about that in a moment. And then the second thing to do is to construct some differential forms that satisfy the first law. And so we can turn the first law in terms of these perturbations into just a geometric fact about one forms, which is a little bit easier for me to grapple with anyway. And as I said, I'm going to deny that. So I'm going to go really briefly through just the geometric setup, and I hope to keep it at a mostly pictorial level, just so that I don't have to get into a lot of the interdimensional algebra. So just take some bundle, whatever your favorite bundle happens to be. I'm going to call 9E over your spacetime manifold, and I'm just going to treat this as a 3+1 dimensional manifold throughout. I think I sometimes refer to it as N. Anyway, so we're going to take this bundle and construct a new one out of it, the first jet bundle, which you get by just focusing on a certain point and then adding information about the first derivatives. So since I've drawn this big picture, you can sort of just look and get all of the derivative information by looking at it. Well, it's a linear function, so it's going to vanish above 1. But if you were just living at P, and you can only see your immediate neighborhood, you would see these two sections, and you would say to yourself, well, they agree, they're the same value here. And if you were just looking at the bundle, that's all you could say. Looking at the first jet bundle, though, you're going to realize that they're different because they have different derivatives, they're going to be changing differently. So this is adding a little bit more information. The second jet bundle just takes us up another, right? First and second derivatives. And again, you're going to say that these agree if you live under the E or the first jet bundle, but the second one you're going to notice the difference. So 1 to infinity, we're going to look at just the entire Taylor expansion about whatever point you're at. And you get the jet bundle. Here's some technically about how you actually define it. But the way to think about this really is you pick some point in your manifold and look up, and you're going to see a Taylor expansion about yourself. So you can talk about functions of the metric and its first two derivatives, for example, and then you can prove things about the only function of the metric in its first two derivatives that satisfy particular constraints is the Riemann curvature tensor. And you pay precise these sorts of claims that one sometimes hears. And you know, as I illustrated before, you take this picture and you can look at it, study it a little bit, and just sort of extract all of the Taylor series information and get a slice out of your jet bundle, which is going to have all of that information. So there's a prolongation of the section to the infinite jet bundle. Okay. So this is a natural place to define the calculus of variations. And this is just personally, I'm much more comfortable with this version of the calculus of variations than the more intuitive versions that I've seen in the past. So the variational bicomplex is just going to be the DRAM complex on the jet bundle. So it's the same sort of exterior differential that you're used to on the space-time manifold, except now it's keeping track of both the space-time manifold and all the fields living on it. There's a natural splitting of this into changes in the space-time direction and then changes as the fields vary. And I'm going to represent the change in the space-time direction with that, and then the changes as the fields vary with their little delta. And so really all I'm doing is just taking the sort of stuff you see when you look at calculus variations, interpreting it in a certain geometrical way, and then getting back what we wanted in the first place, except now I can be a little bit more careful about the sorts of claims I'm making about it. And the important sort of equation that is going to be relevant for us is this global first variational formula. So a variation of the Lagrangian is going to give you your Lagrange equation plus some other form, right? And this is going to be a boundary term. Whenever you do calculus variations, you always integrate these off. And so usually you can just forget about it. This is going to be now an equation of differential forms on your jet bundle. You can treat it much like you would differential forms in just regular manifold. If you're familiar with the way that Wald goes about it, he uses a slightly different, he does this in a number of papers, not just one with Iyer, where he uses a slightly different formulation. And other people use it too. They talk about these locally constructed forms. If you are familiar with it, you can translate between what I'm saying and he says, like going back along this. If you aren't, then just pretend you didn't see this. Okay, so this is the, as I said, the particular formula we're going to be interested in, the equation of first, the global equation of first variation. If you've done calculus variations, you'll recognize it. And you'll also recall that the Euler-Lagrange equations in this form is really all you need to talk about the evolution of your fields. This theta term is pretty extraneous, except if you want to talk about conservation laws. So Noda showed how this, you need to keep track of this if you want to keep track of your conservation. Yeah. So in the interest of maybe giving a slightly more concrete example, let's just look at, sort of something you might see in upper undergrad or graduate differential geometry course. So the Gauss-Bonnet theorem gives you a way to translate between topological facts about surfaces and curvature of surfaces. In particular, if you take any Riemannian metric on a surface, a two-surface, integrate over the whole surface, and you're going to get this topological characteristic out, the Euler characteristic of your surface. We can set this up in the stuff that I was just talking about. You just consider your base manifold to be a two-surface. Think about all the different ways you can embed it into 3D. It doesn't have to, this looks like it's a section. It's not supposed to be. It's just supposed to be any embedding, so it could be a sphere instead or whatnot. This is the details. And then when you run this, when you crank this machinery, it turns out that variations in L are actually exact. And so anything is going to satisfy the Lagrange equations. And so this left-hand side is going to vanish. And so it looks like in the stuff that I just set up, and this calculation which you'll just have to trust me on, I've derived some sort of odd contradiction. But in fact I haven't. And this is the first important point that I'd like to make. What I've done here is just ignore the coordinatization of the various surfaces. And if you take this into account, then you can no longer write this, because this form isn't equivariant, or sometimes physicists will call it manifestly covariant, or something along these lines. If you respect the covariance of this setup, then you're no longer going to have this problem. In other words, if you pay attention to how the form is going to have to patch up over the entire manifold, you're no longer going to be able to do it consistently. And so if there are holes in the manifold, like the Euler characteristic detects, then you're not going to be able to patch up over those. And that's where you're going to start to run into trouble. So we should be invariant under all of these symmetries, including the orientation-preserving diffeomorphisms. And if we consider only the equivariant forms, then we're going to get what we should have gotten, the Gauss-Bonnet theorem. And so the lesson to take away from this, basically everything there's so far, the lesson to take away, is that we have this global first variational formula. It incorporates covariance, and it encodes global information about whatever bundle we're looking at. It tells us how we're allowed to patch things together. And so there's a sense in which we've already incorporated this global information and got rid of locality. But I'm going to go back to it. Okay. So there's the setup. The first thing we wanted to do was rewrite the Lagrangian, right? Well, iron walls to do this. In terms of what we've done so far, what we want to do is show that there's take some Lagrangian that has this signature, rewrite it as that one. And if you think about it without looking like that, not mathematically, it should make sense, right? If you have G and all of its derivative information, you can just reproduce its Riemann tensor in the usual way. You just plug in the equation from Wald 1984 or whatever, right? Textbook. And of course, if you have all of this, you can just forget about the R and get back that. So if you think about it just in terms of the kind of information you have, it should be relatively intuitive that you can go back and forth. And you can translate that thing that I just said into generalized abstract nonsense and draw a diagram and then think about it for a while and realize that it says exactly what I did and it's true. And maybe just don't look at this unless you recognize it. This is a proof of the thing I just said. You could also prove it by doing 5 pages of inductions, but that's tiresome. The important part about this is there's this particular functorial quality to this diagram, which means that as long as you do the same thing to all of your objects, you're going to preserve this intertranslatability. And so in particular, if you restrict attention to equivariant forms, or if you add on matter fields or background fields, or do both of these, then you're still going to be able to translate just directly back and forth. And so if we look at this claim, this isn't going to be able to work out because we dropped this other information on the way. And that contradicts the claim that you can translate back and forth like this other proof shows. So maybe I'm not going to get into all of the details about why that is. Right, so I think that this is just a fact about Lagrangian dynamics in general, and so whether or not you have background fields, you can include this. And it comes from the things that I'm assuming about what general covariance means. I'm taking it to just be equivariance under the diffeomorphism group of M. There are reasons you might object to this, and we can talk about that in Q&A. And I'm taking a background field to be a section of a bundle that just has a trivial action under this, and so it's going to be fixed by any of them. And so the sort of argument that you might give to get rid of the dependence on it is just not going to go through. Because for a background field, diffeomorphism is going to be generated every time as the identity, and so it's not going to make a difference. Okay, so the summary of what I've said so far, and stuff to remember anyway, is that putting in these terms makes it a little bit clearer to me anyway about what the various operators are doing in various places, and it's going to give us a way to talk about what the link is between the operators infinity and the first law and the operators at the black hole horizon. There's this bijective correspondence, from which we should conclude that really, in this discussion, when we're talking about the first first law, we can just consider the geometric sector and sort of ignore matter fields, which is what I'm going to do for the rest of the time. And then assuming what I just said about general covariance, you're not going to be able to get rid of background fields, but that's kind of good, because what happens when you do this whole setup and then get rid of them, you do everything without background fields and then notice that, well, it kind of works in background fields, sort of. If we do these other things, then it's not clear why, and this is just an explanation of why that would be. Okay, so that was step 1. Step 2 is actually defining a notion of black hole entropy that's going to get us the first law. So recall, again, this formula. Variations in Lagrangian are going to give us the Euler-Lagrange equations plus some other extra term. I'm going to pass over that. As I said earlier, according to notice theorems, you need to keep track of this theta to keep track of what the conserved currents are in your problem. And what's going to happen is we're just going to take this form, decompose it in a certain way, and then point out that, oh, that's what the first law is, right? So you can rewrite the first law as just a little perturbation of some quantity equals 0, and this is going to be that quantity. So we've set up this whole... so really, what's going to pop out is that the first law is an expression of the facts about the variational calculus. Okay, so yeah, think about just the geometric sector, forget about matter fields, forget about background fields, think about just the Einstein-Hilbert Lagrangian. There's this conserved current, which some people call the Krinkovich-Witten current, some people call it Eshkar-Trombelli Cool current, or universal current. There's a bunch of names for it. It's all the same thing. Perhaps some of these sound familiar to you. So what we're going to do is we're just going to integrate this over all of space-time. And so what we're doing is we're taking this local quantity. Well, it's local in one sense, right? It's local in that it's a differential form. It's global in that we're being covariant about it. And then we're going to integrate it over all space-time. So now we're getting like even less local, right? Because we're looking at all space-time. How does this look? And we're going to get this omega out. And as long as we're satisfying the equations of motion, all this is going to depend entirely on just how many holes there are in the space-time that we're integrated over. So if we're looking at just a plain old black hole by itself, it's just going to be picking out the fact that there's a hole in the middle of it. And then, alternatively, if you don't integrate it, then you can notice that the symmetry, the rewriting symmetry that we've done, preserves everything that you can possibly say. So it's so far, we have done this rewriting, but it hasn't actually done anything yet. Right, the rewriting, starting with just the metric, rewriting in terms of the metric and the Riemann tensor, they're pretty much symmetric for the reasons that I've said, and so far everything we've done is symmetric under them. But now we're going to break that over. So we took, the reason that we rewrote everything to depend on the Riemann curvature tensors is so that we can decompose variations of the Lagrangian and the Euler-Lagrange equations into parts that depend on the metric, parts that depend on the Riemann tensor. So now we can vary the metric and the tensor individually, and we can define this new quantity, S, by integrating just this bit, the part that we decomposed out over all of space-time. So again, this is a case where we're slicing it up, foliating, and then integrating over one of the entire spatial slices. So looking at all space-time at a moment, and looking at this quantity integrated over all of that. If we have some stationary killing field, it's going to be a symmetry of L, since L just depends on the metric. We're going to need conserved charge Q, and in terms of the universal current I mentioned before, it's going to be closed on shell. We're going to break this down, and it might already be, you can see almost it's peeking through that if we integrate over all of these, the D's are going to disappear, and the first law is going to pop out. And in fact, that's what happens. You integrate over everything, and then you apply Stokes' theorem here, and that's going to allow us to, instead of integrating over all of space-time, we're just going to integrate over the boundaries. The things are going to vanish in infinity, they're going to be non-vanishing at the horizon, and so our integral over all of space-time is going to turn into an integral over the area of the horizon. So the data that we needed to do this were our stationary vector field, the number of holes in our space-time, and how the Riemann curvature tensor varies within the Lagrange equations after you separate out the metric degrees of freedom. Okay, so returning to the two puzzles. There's this question, how do these operators acting at infinity and at the horizon relate? So my response to that is just they're not local at the horizon and infinity. They're both covariant perturbations integrated over all space and time. And so here's the mapping, right? Like they're both descend from this other global perturbation that looks a little bit local, sort of on an intuitive picture of black hole spacetimes. But these are actually global in two ways. First, by the covariance condition, we've had to keep track of sort of what's going on far away that we could be brought closer by diffeomorphism invariance. So sorry if I made you cringe by talking about it that way. But also because we had to integrate over all space at a time, and so we're looking at what everything looks like rather than just like something at the horizon. And now, there's a second question I brought up at the beginning. How do A and the first and the second laws relate? Well, the second law is the area of the event horizon, and we get it by integrating locally over the horizon. So when proving the second law, you look at divergence of a vector field, or the expansion of a vector field at the horizon, integrate over the horizon, and show it's just going to have to increase. And the delta that we wrote there was a finite difference that we get by considering two finitely separated slices of time and just integrating, or just comparing the two of them. However, A in the first law comes about by by just this fact about geometry, where if you look at the whole space-time, is going to be determined by what happens on the boundaries, in particular geometric setups. And so as we integrate this form over the entire spatial slice, it's going to end up just being an integral over the boundaries. It's going to need a killing field, right? And so this is where the time aspect of it is going to come in, because we have to be able to slice somehow, and the slice has to make sense as time in some way. It's going to encode this information about the slice and about the killing field and about variations between the metric and the Riemann curvature tensor. So that's how I'd like to answer those two. But this leaves me with a couple more puzzles. So first, I've been pretty sloppy about what I mean by global and local, and that's just because I'm not totally sure. There seem to be at least two notions going on: the kind of globalness, the kind of non-locality that we get through general covariance, and the kind that we get through integrating over the entire slice, right? And so the question is, can we devise these local quantities in black hole spacetimes? It'd be great if we could, because a lot of the thought experiments that align black holes involve like bringing things really, really close to them and then letting go. And as soon as it crosses the horizon, now our M includes the M, the stuff we dropped in. It doesn't include the S. It can include the J, depending on how you do it. And so there's this odd sort of crossing the horizon that's going to, there's a really strong sense of locality we need to do these thought experiments. But if we can't get a handle, or if we can't get a handle on what that kind of locality really means, I don't really know how to go about thinking about these thought experiments. And this is, I think, an important question more broadly in the philosophical foundations literature. So a lot of the discussion of gauge theories and general relativity have depended on various notions of locality and interplays between them, trying to figure out which theories satisfy which and which ones don't. Of the locality principles I'm familiar with, for Healy, for example, none of them seem to capture the kind of locality that's going on here in either case. I should mention that this last question, that can we devise these local quantities in black hole spacetimes, there was a paper posted on the archive last night that answers this partially. So I haven't had time to completely digest it, but the answer is yes, sort of. But there's these funny things that go on because you get these quantities that only are intelligible when applied to particular spacetimes and not others. And so it's just there are these properties that some spacetimes just can't talk about them having. And it's also not clear to me exactly what kinds of quantities you can get out of this. But as I said, I can only read it briefly over breakfast. The second puzzle that is sort of a much more general one, and it's part of what motivated me to look at these problems. So most of the evidence we're supposed to take from black hole thermodynamics comes from these thought experiments about dropping stuff into black holes, either from far away or from close by, thinking about the radiation buoyancy that we're going to get near the horizon. And I suppose I lack the physical intuition in most cases about how these things are going to act, and so I would like to get a little bit more of a handle on it. So I'd like to see what's the strong analogy that we're getting between thermodynamics and black holes, more than just the formal analogy that we're getting in the equations. And now it seems like I'm not sure what version of entropy I should use. I could use just the black hole horizon, but then that's going to work only in some cases, and it's not going to work in the cases where things change, basically. The Wald entropy is much nicer for that reason. You can be defined in pretty much in any spacetime that has a time-like vector field. But now it's this global quantity that sort of is the entire spacetime slice or the field at a time. And now it doesn't seem like you can really drop stuff into the spacetime, right? It's either in the spacetime or it's not. And so at what point, do you start taking account of it in the property of the metric and Riemann tensor? So these are the puzzles that I would like to leave you with.
I apologize for not getting this earlier. Is there any restriction on the kind of dependence on the higher derivatives of the metric and the action? Because I have a memory that the Wald business only works for certain kinds of dependencies on, like if you have a function of R mu, then it applies to that situation. I can't remember how much more general it goes than that.
Right, so it applies to, it's going to apply to any, it's going to apply to any theory, covariant theory of that involves just the metric. But the important restriction that I think we're talking about is that this L that depends on the Riemann is going to, it has to be the case that it agrees that if you swapped in the this expression every time, I didn't write it out, it turns out. If you swap in the Christoffel symbol expression in terms of the metric for the R, then you're going to get the same value. So in some sense, it depends only on G. But the sense, it's determined entirely by what happens on the sub-manifold of this, such that R is the Levi-Cuvita curvature of the Levi-Cuvita connection of G. And so there is a restriction on L.
So
the answer, yeah.
Or
sorry?
What would a physicist call that, having a torsion-free spacetime? Or
What would they call it? So
I'm just not very familiar with the language.
Right, yeah.
Jet bundles, I apologize.
No, it's not.
So you said there that it could be a functional of G of grad R or grad R. So that...
Right, let me find my... Sorry. Here we go. This is basically...
Right. So that would seem to imply that it works for arbitrary effective Lagrangian, right? Because, well, as long as you can build everything out of R, I suppose.
Yes.
Riemann, I mean.
Yes. And so the standard thing to do when applying this is just take the variation of L with respect to R.
Right, that's what a physicist does with the Wald formula.
Right,
you
that's
take
right, yeah.
the action by the R
and
plug in some other things, and that gives you the answer.
Yeah, and that ends up being the same thing as what I did. So the reason to go and think about this rewriting is because if you want to define the variation with respect to R, then so in the Wald paper there needs to be this sort of, well, first you vary R as though we're dynamical, and then you say, oh, but it's not dynamical, I'm going to rewrite it in terms of other things, and then, oh, maybe it is dynamical, right? And so basically this is saying it's dynamical, this is saying it's not, but because we're saying we're always going to agree, because we're doing this rewriting back and forth, it's going to work out such that it sort of doesn't matter. Really, this is accounting for the sometimes it's dynamical, sometimes it's not business. Yeah.
This is kind of out of left field, but when Eric was worried about this connection between the properties of the event horizon and the sort of asymptotic defined quantities, one thing I started thinking about but never got very far in looking at is in proving black hole uniqueness theorems, you similarly have to make assumptions. Usually you assume that the metric is actually analytic in order to show that you get a unique Kerr solution when you have the, these are just sort of no-hair theorems, right? That there's going to be unique external domain for the interior spacetime, and so then you have this really strong assumption of analyticity that makes this connection. Now, I was curious whether the ways in which you're saying that they're globally defined quantities, that's presumably a lot weaker than assuming that the spacetime is analytic in the way that they have in the uniqueness results.
Yes. Yeah.
But there's still a kind of global. So could you say more about how strong? So your main line of arguments, there's these global properties. The entropy in particular is a globally defined property, and that's what gives you the link between the horizon properties and the asymptotic properties. Right?
Yeah. So here's another sort of global-local connection. When you do the black hole uniqueness theorems, you show that most reasonable black hole spacetimes, all of them, I don't know, are rigid.
Yeah, there's some set of assumptions.
Yeah, they're rigid in a certain way, which is that so normally the event horizon is a sort of global property, right? It's whatever region is going to be blocking off things from going to future infinity.
Right.
And so how do we talk in terms of the horizon? Well, you show in the rigidity theorems that there's you're always going to have a killing field that vanishes on the horizon or goes off. And so that's going to give you a local characterization of the event horizon using this this vector field. And so you're going to have this sort of analyticity going on. So that's one notion of this global local link. The one that I'm putting out is slightly different for the following reason. It applies not just to black hole spacetimes, but to any spacetime that you have a foliation of. Right? And so you still have a global character because you're integrating over the entire thing. When you focus on black hole spacetimes in particular, then you are able to express the integral over the whole spacetime in terms of properties of this connection, this vector field, the killing field. And so you get to use either connection between global and local in those cases. But this is going to apply much more broadly, and so even in cases where you don't have that rigidity, you're going to have the global thing.
Do you have any ideas of what this might mean for the microscopic degree of freedom? I know this is mostly classical, but...
Right. No.
Okay.
Yeah.
It's kind of maybe totally relevant and not related. I was wondering if you have a region of space-time with a black hole in it, how are you integrating any forms at all on how to
yeah, that's an excellent question. Well, so you need to make certain assumptions about boundary conditions, right? That things are vanishing outside of a complex set. And so at least at infinity, things are going away. When you're looking at the, when you look closer to the singularity, I suppose, you just use sort of whatever shell you like around it in order to integrate. So you apply Stokes' theorem, but there's this problem. Hold on, I don't have the appropriate space-time region to apply Stokes' theorem, right? The boundary, there's this funny thing going on with the singularity. And I've actually never seen a sort of satisfactory treatment of this. Normally it's just sort of, well, you know, it's a whole slice, and so you just integrate a whole thing. So, I mean, the short answer is just sort of pick any shell you like, and they're going to end up being the same, because the killing vector connection, right? You express things from the killing vector, and then it's going to change inside of the black hole. And so as long as you're just integrating over the outside, you're going to end up with the same. But, you know, I just might not.